as I was saying, I'm going to move a little bit away from the textbook, some stuff from the textbook. I'm not a fan of how Chapter 8 does it, but what we want to talk about is a little bit about how batteries work and how circuits work. And we're going to start out looking at something called Ohm's law. Ohm's law is the mathematical relationship that explains batteries. So here we go. Some definitions. A coulomb. A coulomb is a unit of electric charge. Charge is measured in coulombs. 1 coulomb is huge. If you absorbed 1 coulomb of charge all at once, you'd almost certainly not survive. Now, if we spread it out over a month, yeah, no problem. But if you picked it all up at once, that would not be good for your body. And we will later on talk about how electrocution works and what the dangers are. It's both important, cool in a creepy way, but good science. If an object gains 6.25 times 10 to the 18th electrons, that means that means if you multiply 6.25 times a 1 with 18 zeros, which really means 625 with 15 zeros, whatever heck, a big number, it gains 1 coulomb of charge. Potential is the ability to do something. My mom says I have potential. Yeah, casual, we're talking in the science sense. In fact, we're going to be talking about something called potential energy, which is stored energy. So potential is the ability to do something. Energy is the ability to do work. Now, work, Hudson, in physics has a very, very specific definition, but I'm not going to get into that right now. But basically, it means you can make something move if you want to. It means you can apply a force over a distance if you want the physics definition. Or it means that you can change its energy motion state. But that's a whole, you know what? Energy is the ability to do work. And then there's something called the law of conservation of energy. It dominates your life. In fact, it's probably one of the 3 or 4 most important principles of the universe. And it says this: energy can't be created or destroyed. It can only change form. So heat is a form of energy, light is a form of energy, sound is a form of energy, motion is a form of energy, nuclear power is a form of energy. You can transform energy from one type to another. And what we're going to be talking about is transforming electrical energy. Actually, let me phrase that. We're going to talk, Riley, about transforming chemical energy into electrical energy into toys. Moving things, power, our infra system, our whole grid system. Potential energy is the stored energy in an object. This battery that I'm holding has some stored energy, some potential energy in it. Why? Because if I set this upright, I can use this battery to do me some work. Whether it's power a calculator, or make a toy car move forward, or I could put this in an electric motor and get it to lift something up. I can get it to do useful work. So, electric potential energy is stored electrical energy. Batteries contain electrons. Probably, Nicole, quadrillions or quintillions of electrons. And they're released when you turn your iPod back on. Now, for this to work, what we have to do in here somehow is separate the electrons from the protons, separate the negatives from the positives, because unlike charges, what? Attract. What we are going to do is we're going to separate negatives from positives. They want to flow back together because they're attracted to each other. We're going to block them from moving back to each other in here, and instead we're going to connect a wire here and here. We're going to force them to go through the wire to get back to the positive. That's how circuits work. Electrochemical cell. what we call a battery in everyday life. And they store chemical energy that gets converted to electrical energy. What's going on inside here, Youngjun, is a chemical reaction that is very good at separating electrons from atoms and giving you a buildup of negative charge and then doing something with it. We'll talk about how that works. In fact, we'll make a very simple battery of our own next week or the week after. You'll build your own. It's actually surprisingly simple. Technically, a battery is a series of electrochemical cells, connected together. Technically, Aiden, here, look up. Technically, this is not a battery. Technically, this is a battery. One cell, a battery. I'm not going to be that fussy. We're going to call these batteries because that's what society has really done. So I won't take marks off if you say, Mr. Dueck, can you hand me a battery? I'll know what you're talking about. All right. What do you think has more potential or stored energy? I'm going to give you a couple of situations. Let me pause the video. So what do you think the correct answer? Which has more stored energy, A, B, C, or D? Think which would do more damage if you let it go, A, B, C, or D? Okay. What we're really saying, Lyndon, in physics is which would do more useful work? D. Okay. One of the ways that we can store energy is to have a mass at a given height. It's how hydroelectric dams work. We build the dams in the mountains, we let the water build up behind the dam so the water gains height, and then we drain the water, and as it loses height, we can bleed the energy off. We're very clever that way. So it turns out the potential energy due to gravity depends on two things: the mass of an object and the height of an object. The higher and heavier something is, Omid, the more damage it'll do when it hits the ground, the more work it can do. Here's what I want to get to. The higher and heavier something is, the more stored energy it has. Well, it turns out in electricity, there's a similar concept called voltage. Voltage actually, Kiana, is a really tough concept to wrap your brain around, and I know many people in physics still don't understand it well. I don't have a great grasp of it, but voltage is sort of like height. When you say this battery is 12 volts and this battery is 6 volts, what you're really saying is this 12-volt battery is capable of doing more work. It's got more stored energy in it. And I've already told you something that's technically wrong, Riley, but it's mostly right, and we're not going to be that fussy. So, again, energy is the ability to do work. And there are two main types. Kinetic energy, which is the energy of motion. Anything that moves has energy. Really? Yep. Pause the video. Second type of energy is potential. Any moving object has kinetic energy. Potential energy is the energy that is stored in an object. For example, water behind a hydroelectric dam has gravitational potential energy. If we allow it to fall, maybe even if we're clever, we'll build a tunnel inside the dam itself, a pipe that the water can go down. We can get it to turn a generator and turn it into work, useful work, electricity. But we're not making energy out of nothing. The water had the energy in the first place, and we bled some of the energy off. Batteries, it turns out, contain a stored energy called electric potential energy. Why potential? Because it's stored. Why electric? Because it's going to be electrons moving around. It's stored because we have moved some electrons into a position that they're not happy with. In fact, you can sort of say, Tristan, and this is where my analogy breaks down, what this battery does is the same thing that I'm doing right now to this bowling ball when I lift it up to a height. I'm giving it more energy because when I let it go, it'll do more damage. Damien, basically, what a battery does is it lifts electrons to a height. Now, it doesn't make sense because this battery is only this high. It's an analogy, but casually, you can kind of think of it that way. What a battery does is it raises charges to a location where they want to, I'll say, fall down. That's not quite right, but they want to get back to where they came from. Sort of. And there's a fair bit of energy stored in these batteries. More than you realize. Put your pencils down. So hopefully I've convinced you there's a fair bit of electrical potential energy stored in a battery. So, back to our notes. It turns out that when unlike charges are moved farther apart, they gain electrical potential energy. Sort of like when you lift an object higher and higher, when you let it go, it will do more damage, Lyndon, when it hits the ground. Sort of. The analogy is going to break down, but I'm going to, at least to help you wrap your brain around it, treat voltage kind of like height. Okay? Well, sort of like stretching a spring or an elastic gives it stored energy, and when you let it go, it wants to spring back, return to its original state. Or like lifting an object to a height. In a battery, the unlike charges are electrons and protons. Electrons, it turns out, are removed from one end and sent to the other. And this creates something called electrical potential energy due to charge separation. Again, Kiana, what's sort of going on inside that battery chemically is pretty similar to me doing this and then letting it go. Except what the battery can do is it can store it here for quite a while. Is that okay? And again, you understand, I'm using that as an analogy because it's pretty clear there's not really any height in, but chemically that's what it's doing. It's raising those electrons to a higher energy state, and they want to get back to their original state. The same way as when you stretch a rubber band, if you let it go, it wants to return to its original state. You okay with that? The unlike charges attract each other. Sort of like how when we lift something, it wants to fall back to the earth. And I'm picking my words carefully, Aiden. I keep using words like sort of like and kind of like because this is actually technically completely wrong, but it's a good analogy, Amelia. It helps you wrap your brain a little bit about what's going on. Some terminology. The terminals of a battery are the endpoints of the battery where we make a connection. For big rectangular batteries, often there's actually two terminals that are marked, like on a car battery. Where are the terminals on these kind of batteries? What's the top, positive or negative? This is the positive terminal. Okay? Negative. By the way, if you actually take these apart, it isn't this section positive and this section negative. Actually, there's a positive terminal that runs down the center, and the negatives are all around the outside and connected to the bottom, but we'll talk about that. I'll show you a picture, I think, later on. Extra electrons accumulate on one terminal, making it negatively charged. So the purpose of a little picture here, the purpose of a cell or battery is to give electrons stored energy. The other terminal has lost electrons, making it positively charged. By the way, the protons don't move. And again, this is why I said Cadgel, Ben Franklin was the one who named electrons negative and protons positive. He named them backwards. It would have been much nicer if he'd said electrons were positive, because it would be much nicer to think in terms of positives moving around instead of losing negatives, and you have to say, well, it's a minus minus, which is a plus. But we're stuck with it. A circuit. Oh yeah, turn the page. Here's a standard circuit. Okay? This allows, I don't know which of these is positive, which of these is negative, but just in my drawing here, I didn't include this picture in your notes, did I? Okay? So maybe that's the negative and that's the positive, which means electrons are flowing this way, this way. Now, they'd like to be able to go straight this way, but we block them right here. We force them to go through our circuit, and we can bleed off the energy. They lose some energy going through here. Now, you asked, why do things heat up? If you do this, what happens to your hands? If electrons are racing through a wire, they're bumping into other atoms along the way, similar to doing this, and that's what causes wires to heat up. Most circuits give off, we lose some energy to heat. Although we have something called superconductors, which we're hoping to build our technology on. Those have perfect conductance. Electrons can flow through, losing no heat. But right now, we can only create superconductors by cooling them with liquid nitrogen. Hey, you want to be more powerful than Bill Gates? If you can invent a room temperature superconductor, they'll be talking about you for the next century or so, because then a lot of our electrical technology would be dramatically improved. So, in fact, this is how a light bulb works. The reason the light bulb glows is the electrons going through there so fast bump into other atoms and generate enough heat that it glows, red hot. We lose some energy, and eventually they end up there. Now, this battery only has a certain number of electrons. A few, this is going to sound silly, but a few quadrillion electrons. Few quadrillion? Well, yeah. So eventually, when you run out of extra electrons, what do we call that battery when it no longer works? Dead. We say that's a dead battery. You can recharge them, and in rechargeable batteries, what you're doing is you're reversing part of the chemical reaction and re-separating the charges, but that's why there's no such thing as a battery that lasts forever. You're bleeding off electrons constantly here, and eventually, no more left. Batteries. To make a battery, what do you need? Turns out you need two different metals. These can act as terminals, or fancy word, electrodes. And actually, that's all you technically need, but this would be a lousy battery. If you touch two different metals together, one of those metals will be more electron hungry than the other metal, and so some electrons will flow, not very many. But for example, if you put two metals side by side and you leave them there for a long time, you'll notice that electrolysis occurs, and eventually you'll see some corrosion. Like by a long time, Kiana, I mean over months. Usually, to get a better reaction, we have something called an electrolyte. This is an acid or alkaline paste, something that will allow electrons to flow from one terminal to another. Put your pencils down. I think I have a big stretch. Pardon me? Didn't get what? The last flow, I think. Oh yeah, I underlined the word electron. Sorry, it's the word flow. You could probably just figure it out by reading, though. I'm probably.
No, I didn't see it.
Okay, flow. Just saying. So, again, this is going to be repetitious, but I'm repeating myself on purpose. There's a reason I'm repeating myself. The repetition here is intentional. See how I did that? I repeated myself 3 times there? No? Okay. Energy called electric potential energy. It's stored by the electrons. In fact, really, Damien, it's stored by the separation of electrons from some positives. The separation of charge is the generic term that we say. When you stretch an elastic, you're storing energy. It'll be released when you let go. The more you stretch it, the more energy you store, and the more it will hurt when you let it go. Some more terminology. Voltage, which is also called potential difference. That's sort of more like my height analogy. We're saying, oh, when you lift something up, there's a difference in height from where it is and the Earth's surface. Voltage, there's a difference in what we call electric potential. You've separated charges. It's sort of like height. Definition. Here's the actual proper definition of voltage. It turns out it's the amount of electrical energy per coulomb of charge. The amount of electrical energy per coulomb of charge. Basically, it's related to how much energy each electron has. So, Rihanna, here's a battery. Riley, catch. Don't drop it. Here's a battery. Here's a battery. Here's a battery. Now, I've given you 4 different batteries. I think I've given you a AA, I think a C, that's also a C, and that's a big D. Obviously, they must have different voltages, right?
Used before March 2000.
That's fine. Obviously, they must have, they're dead, but look at them. Those of you that have the batteries, read the voltage. It's on the side somewhere. Obviously, with those different sizes, they must have different voltages, right? How many volts? Shh, guys with me? How many volts? 1.5. Lyndon, how many volts? 1.5 volts, really? Well, this small one must have less than, how many volts?
1.5.
What? How many volts? It's on the side somewhere.
It says volt.
Or a V.
Feels like a V.
Mine says volt. Maybe
Okay.
1.5.
Come back. So, wait a minute. All these have the same voltage? Yeah, they all have the same voltage because all of them give each electron the same amount of energy. Well, then what's the difference? Oh, which battery has more electrons to give? This one or this one? The small one or the big one? Which battery will last longer? The big one. They'll both power the same toy. This one will last longer. Well, why don't we just put these in all of our toys? What's the trend right now towards electronics? What are we trying to do with electronics? Make them what? Smaller. So we're trying to cram more electrons into these so that maybe they'll last longer. But we're not making them more powerful. It's 1.5 volts all the way across. Okay? Even I just replaced a little watch battery, and I actually put a voltmeter on it yesterday because I was curious. 1.5 volts, a little tiny watch battery. It does change the rectangular ones with the 2 terminals on the tip that you probably touched to your tongue at least. Those are 9 volts. Okay? Which means, oh, in that system, you're giving each electron more energy. And what's the voltage in a car battery? Anybody know? Nope. Car batteries. Car batteries are 12 volts. Okay? So there, you're giving all the electrons even more energy. And there are some batteries that have higher voltages than that, but not that many. Those are the standard ones. Voltage is also called potential difference. And the fact that I use such a big font probably means that was important. Probably means a good multiple choice question might be, what's another word for voltage? Or a good fill-in-the-blank question. Voltage is also called blank blank. Okay, I've given you batteries and you read on the side, but how do we measure voltage? Well, it turns out we use a little device called a voltmeter. And it measures the potential difference between two locations. We use a device called a voltmeter. And it measures the, by the way, what's another word for potential difference? Voltage. You see, how many volts was in this one? Okay, 1.5. I don't think that this right here is 1.5 volts and this is 0. I suspect this right here might be 4.5 volts and this is 3 volts. But what's the difference between 4.5 and 3? 1.5. Or maybe this might be 11.5 volts and this might be 10 volts. What's the difference? This is what a voltmeter measures. It doesn't measure voltage. It measures the difference in voltage between two locations. The potential difference. The difference in potential between two locations. We're getting technical here, but hopefully, Lena, at least a little bit interesting, like, oh, I didn't know this is how the system worked. Think of potential difference or voltage. Oh, no, sorry. As the height of an object. In fact, we're going to use that to analyze circuits. We're going to treat every circuit like a ski hill, where the mountain is the chairlift, is the battery, is the height, and the skiers are the electrons wanting to return back down to the ground. And it turns out you can solve really, really complicated circuits intuitively by skiing down the circuit. The amount of charge separated is like the mass of the object that has been lifted. Pause the video for a second. So far, so good? How much more am I going here? Ooh, boy. Lots. I'm trying to think about when I want to pause for a second. Electrical energy depends on both the voltage and the amount of charge separated. Depends on both the voltage and the amount of charge separated. Again, looking at this AA, or this is a AAA battery actually, looking at this AAA battery and looking at this D cell, which one has a higher voltage? It's a trick question. Which one has a higher voltage? It's a trick question. Okay, they're the same. Which one has more stored energy? Why? Because more electrons have 1.5 volts. Fewer electrons have 1.5 volts. So, AA or AAA, have you ever looked at the voltage? We just talked about this. I don't think this is in your, is this in your notes? I don't think it is. Oh, is it? Okay. Turns out they're both 1.5 volts. Hey, you can fill in the 1.5. What's the difference between them? Key idea, what's the difference between them? Oh, I don't want that. A bigger battery, what? Same voltage, so what's the difference between them? Has more electrons, stored energy, and so it will last longer. But it's bigger. We don't like bigger. We like smaller. In fact, one of the ways that your cell phones have gotten around this is they don't build batteries in this shape. They make them flat and rectangular, and that allows you to make it even thinner. That's a different type of technology approach to a battery, a different type of chemical reaction. Yeah, that was science. I'm okay. Okay. So, a AA battery I wrote here is bigger than a AAA battery, so it separates more charge. Is that what I said? So it separates, oh, just the word charge. Sorry. So it lasts longer. In that picture, one of those doesn't belong. Which one?
The really, really, really small. Or no, that's one of two. The one with, yeah.
That's a 9 volt. By the way, all a 9 volt is 4 1.5 volts stacked, because 1.5 times 1.5 times 1.5, sorry, 1.5 times 4, 1.5 plus 1.5 plus 1.5 plus 1.5, 9 volts. Which is also why it's that weird shape. It was easier to build them that way. Okay? So, why would you want AAA batteries? We like our tech smaller. How many of you have ever seen what we call a brick cell phone? You know what I'm talking about?
Yeah.
Right, the first ones, okay? They were about yay big, right? And they were impressive. I worked on construction. My dad worked on construction. And so for the first 30 years of his construction work, there was no phones on the work site. My mom knew that if there was an emergency, she couldn't get a hold of my dad because you were working on buildings where the phone lines haven't been put in yet. Maybe there was a payphone down the street somewhere, but you couldn't call it. You could call out from it. And I can still remember when my dad, holy smokes, this is great. We got a cell phone on site, this big brick, but it allowed him, for example, to be able to order lumber without having to drive to a business somewhere else and, may I borrow your phone? It allowed families to call in for an emergency. Wow, it was amazing. And now you look at those things and you're like, who the heck would be, wow. In fact, you guys are complaining about your cell phones now. Well, no, actually we went too small. Now the trend now is going with the screens a bit bigger, right? So, D cells, that's these. By the way, you don't need to memorize this, but if you look, it does say right there, the big letter D, and beneath it, 1.5. The abbreviation for volts is capital V. Also carries a potential difference of 1.5 volts. How is it different from that? Right? It can store way more electrons. So when would a D cell be useful? What's the difference between them? When would a D cell be useful? Think about where you still use, or there's a common ordinary device that I know still uses these. Yeah? Okay, why? Flashlight, why? When we need something to last a long time without recharging. Let me move this. Yoink. By the way, look up. How many volts? How many volts? Look, 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 look. How many volts?
3.
Yes. This is why that height analogy still sort of works. This is why in a flashlight, the battery's going, because a 1.5 volts isn't really enough to get that bulb to burn bright, or if you did, you'd be draining the electrons from here really, really, really fast. Oh. 3 volts, or even more. You've seen mag lights that have multiple batteries all stacked together. Here's a picture for you. All of these columns of water are the same height. Lena, same voltage, because I'm saying voltage and height are kind of the same. Which of these do you think is like a AAA? Which of these is like a AA? Which of these is like a D cell battery? Right? They all the same height, but if you punctured each of these and let them drain with the same leak, which one would last longer? The D cell. Okay? You wouldn't be getting more leak from it or anything like that, but it would last longer. So it says this. Which has more energy? More, you know what? Don't write blue on blue, Mr. Dueck. That's hard for them to see. Here's the most energy. And here's the least energy. Same voltage, though. Each electron has the same amount of energy as every other electron, but the right-hand one has way more electrons and therefore more total energy. You're really going on a big song and dance about that. You know what? I've found voltage is a really tricky concept, Lexi, who's going to put her phone away, to wrap your brain around. It's pretty obvious if you haven't figured out sitting up here when kids are looking at their phones. So don't do that. Your phone wasn't even out? Oh, your head wasn't even down? Yeah. Okay. Oh, I think I have some blanks here. Nope, never mind. Oh, yeah, which has more energy and why? So which has more energy? We wrote it on here. Why? More water molecules, in our battery analogy, more electrons. So which has more energy? You okay with that? Why? Well, if we're talking about a battery, this has more electrons. Each electron has the same amount of energy, but where's my AAA? Here, AAA. I put it somewhere dumb. There it is. Maybe this has 5 electrons, but this has 50 electrons. By the way, 5 quadrillion, 50 quadrillion, or more than that even. But maybe this has 5 electrons. Each one has the same amount of energy. But if this has 50 electrons, each one has the same amount of energy. But the total energy is... But each electron can only do the same amount of work as this guy. Right? Because each electron has the same amount of energy as each electron in here. Video, laptop battery fire, which I apparently put on here twice. I don't know why. I want to see it again! How much am I going to get here, Mr. Dueck? You've been talking for a while. 1 page and it's not long. No, we got 25 minutes. Oh, no, you're right. We got 15. Sorry. I can't add. Let's finish this, and then then on Wednesday we can do a lab or two, okay? I know I've been talking lots. Sorry, Thursday next week. I only see you once next week. Yeah, I know. I'll miss you too. No, I won't. Sorry. Aiden, you gonna make it? You gonna make it? Yeah? Well, I just boggled the minds of my grade 9s. Producing voltage. There are 2 types of electrochemical cell batteries. We have what we call wet batteries and dry batteries. The wet ones, you have to add water or some liquid. Car batteries are wet batteries, for example. I think it's wet and dry. Is that what I wrote here? Yeah. Okay. Car batteries, the really, really big ones, the batteries that are so heavy that they're awkward to lift on your own, most of those have some kind of lead-type chemical separation of charge, chemical reaction, and often they need water. Okay? Dry batteries, these ones here. Now, by the way, even the word dry is a bit of a misnomer. There is a paste inside here acting as an electrolyte, but we don't have to add water, what we're saying. Most new car batteries now are completely self-contained and you don't need to top up the water. But certainly when I was in high school growing up, you checked your oil on your car, and one of the other things you did is there was a little plastic, you popped it up and you looked in your battery, oh, it's getting dry, and you just poured some water in there, popped the lid back on, just like filling a water bottle, basically. Turns out an electrochemical cell needs 2 electrodes, and we're going to actually do this probably next class, usually metal, and an electrolyte which allows electrons to flow between them. The electrolyte simply is very willing to pass electrons from one part to another. In a dry cell, the electrolyte is a moist paste. In a wet cell, the electrolyte is a fluid, often water. Although in the newer ones now, they come up with better systems than that. The other problem with the old batteries that used water was up north in the winter, that wasn't a good thing. So now they add stuff to the water or they use a different liquid. Put your pencils down. Knew I had a couple of more videos in here.